The topic of this presentation is change in elastic modulus during fatigue bending and torsion of glass fiber reinforced polymer. The research conducted was carried out actually by 3 universities, 2 from Poland, which are Opole University of Technology and Wrocław University of Science and Technology, and from the German side we had Chemnitz University of Technology in our international cooperation. Preparing a short background like the literature review, we know that when we think about the fatigue, when we determine the strain fatigue characteristics, especially the strain ones, it's necessary to know the elastic modulus in case of bending or tension compression, or shear modulus when we think about torsion. In general, usually, like in the classic propositions, the elastic modulus is assumed to be the same one as the one used in the statics. We assume that there is no change during this analysis, during the fatigue bending, for example, the modulus doesn't change. Of course, there is a moment when the microcrack appears, the modulus decreases. We know about it, however, it's a separate topic, it's the subject of separate observations. However, everything which was said until now, it's still talking about isotropic materials. However, in this presentation, we would like to talk about composite materials, which sometimes behave completely different to the isotropic ones. However, let's take a look at those equations which are presented at the bottom of this page. Of course, the first one is Manson-Coffin-Baskin, and the second one is Ramberg-Osgood, which are like the basic equations which we use when we analyze the fatigue of materials. And in those equations, those two modulus, which are now in red circles, are constant and the same as in the statics. However, already some researchers found out that it's not a good idea to use the constant modulus for the composite materials. So they suggested that we could use a dynamic value which changes when the cycles increase. Here at the top of this page, we can see the equation for this dynamic Young modulus. And then when we analyze the degree of damage, there are 2 propositions at the bottom of this page. They come from 2 different articles. As you can see here, we use the dynamic modulus. And here E0 is the Young modulus at the beginning, and then E as a function of n is it depends of a number of cycles, of course. So in general, and the EF is the Young modulus at a certain way of damage, and when the material damages, this is the Young modulus in this moment. As you can see here, there are very different ways. Like the first one was just a proposition, and here we can see another 6 possibilities how to determine this changing this dynamic Young modulus. As you can see, they are different, and there are 2 things which we could say. First of all, it's that they come just from tension compression, not from bending, not from torsion, just in the simple tension compression. This is the first thing we should look at right now. And the second thing is that they are so different that it's hard to say which is the best. And of course, composite materials, it's such a wide topic. We can have different reinforcement, different materials, different percentage of reinforcement, for example. Depending on which material we use, perhaps we could use another proposition. So, summing up what we have found out from the literature review, the aim of this study is to determine the method of changing the longitudinal and shear stiffness modulus during cyclic bending and torsion, with an increase in the number of cycles, which is different to the current ones, which were only for tension compression, and we didn't know which is the best one, so we are carrying on this research and looking for maybe a better solution, maybe not. We'll see it actually in the future. The analyzed material, it's not very important what exactly was the matrix, what was the reinforcement. However, what is the most important is that these were the continuous glass fibers which were laid up unidirectionally. So these are two pictures of it. I think that the one on the left shows us more about the material. As you can see that the reinforcement is equally laid up in the material. Here we have some basic parameters. Of course, the density of the material is low, as it's typical for composite materials. From here, I would like you to see the second and the third lines, which is Young's modulus and shear modulus, which we're calculating based on the rule of mixtures, which is presented on the right of this page. As you can see, the value of the modulus in the composite depends on both modulus of both fibers and matrix. F is for fibers, M is for matrix, and and also based on how much reinforcement we have. So based on it, we could assume a value of the Young and shear modulus in this composite. The specimens which we were taking into account are two types. For bending, we had specimens of constant cross-section, and here we have for torsion the Diabolo specimens, which scheme you can see on the right of this page. These are typical specimens which were used in our tests. And here you can also see the fatigue test. It's worth saying that we use the controlled deformation in both examples. And on the left you can see the photo of a specimen during bending, and on the right you have for torsion. Moving on to the experimental data, let's take a look at the graph presented on the left of this page. This is a function of the bending moment as a function of number of cycles. What's interesting in this graph is that when the strain amplitude is low, then it doesn't change so much when the number of cycles increase. However, when the strain amplitude was the biggest at the beginning, it decreased so much that it was actually the lowest at the end. And on the right side of this page, we can see that based on the basic formulas from strength of materials, we can derive the formula for the Young modulus, which was used in the next stage of the research. And here you can see a very similar graph. However, here we have torque as a function of number of cycles, and here there's another very interesting fact, let's call it observation, that when we get to the 10,000 cycles, no matter what the strain amplitude is at the beginning, the torque is actually equal no matter which strain amplitude was at the beginning. And on the right of this page, you can see that our formula suggestion for the shear modulus. Here are two graphs. They are very similar to the two graphs which were presented before. However, on the y-axis, you can see the Young modulus or shear modulus, depending on if we have bending or torsion. So the appearance of the graphs is similar. However, the values are totally different. Right here you can see that we have another graph, and they were presented in such a way that for basic characteristical points we prepared sets of data. For example, for degradation equal to 5%, for all of those 6 curves which are presented like on the previous slide. So for degradation 5%, 10%, 15 and 20, we prepared curves which are which have a dependence of strain to the number of as a function of number of cycles. And then the fatigue characteristics based on it were prepared. As you may see, in this case, the degradation 5 and 10 and 15% were parallel to each other. And a similar analysis has been prepared for the torsion. And here, however, you can see that for degradation 5% there is one shape of this curve, and for 10, 15 and 20 they are parallel to each other. Getting to the conclusions, we can see that first of all, based on the literature review, there are several propositions for fatigue, tension, compression of composite materials, how to use this, how the Young modulus changes. However, for bending, there were no propositions found, and for torsion, there was just one, so well, it's not much yet, actually. The second conclusion is that when we talk about torsion, in this case, it's worth saying which material it was. It was PA6 thermoplastic matrix with continuous glass fibers, but we hope that it would be also true for other materials, this way of thinking. However, for this material, we found out that no matter what the strain amplitude was, at the level of 10,000 cycles, we obtained actually almost the same torque. And in the case of bending, we found that when the strain was smaller, then it decreased just a little bit. However, when the strain amplitude was bigger, it decreased actually rapidly. And the last conclusion is that it can be seen that during bending, the slope if the slope increases from 5% to 20%, which was assumed as a failure criterion, then for the larger strain amplitude, the increase is about 5 times, and for the smaller amplitude, it was about 10 times. And the opposite rule was for torsion, where we had a situation that if the slope moves from 5 to 20%, then for the larger strain amplitude, the increase in estimated fatigue life is 100 times, and for smaller strain amplitude, the increase is about 10 times. So there are some rules which we should think about in the future and wonder why and how to take everything into account. Thank you very much.